Hello, welcome to the NPTEL online certification course on deep learning. In last few lectures, we have talked about one tool of deep learning, which is autoencoder, and you have seen that we have talked about the various versions of the autoencoder, like under complete autoencoder, sparse autoencoder, denoising autoencoder, and so on. And we have also talked about how the autoencoders can be trained or pre-trained layer by layer, and then of course you have to have a final round of training, which is end-to-end training. What we have seen in case of autoencoder is that the autoencoder represents the input signal in a compressed domain, where the dimensionality of the compressed domain representation is significantly lower than the dimensionality of the input raw data. And while doing so, the autoencoder tries to capture the salient features or important features of the input data, and it tries to discard any sort of redundancy which is present in the input data. And we have also seen that how the autoencoder output compares with the output of principal component analysis. And we have observed that under certain cases, the principal component analysis output or the principal components of the input data and the encoding output which is given by the autoencoder, they almost converge. We have also talked about some applications of the autoencoder, like we can use autoencoder for classification purpose, where the decoder part of the autoencoder is not used. So, once the autoencoder is properly trained, then the encoding half of the autoencoder, that gives you the compressed domain representation, or it gives you the output which are salient features of the input data. And using those salient features, now you can go for classification or understanding of the input data. And the various applications of such classification can be, say, image segmentation, where every pixel of within an image can be classified into one of the given classes. So, once every pixel in the input image is labeled with a class, then the collection of all the pixels which are labeled to the same class forms a segment. So, segmentation is one of the applications of such autoencoder. Similarly, we have also said that autoencoders are widely used for anomaly detection. So, how is it used for anomaly detection? When you train the autoencoder, you train the autoencoder with all the inputs which are normal inputs, they are not abnormal. So, as the autoencoder is trained with those normal inputs, so now any instance of the normal input, if it is fed to the autoencoder will be able to reconstruct that input faithfully. But if any input or any part of the input image or the video which the autoencoder has not seen before, that means while training, such inputs are not fed to the autoencoder. So, those parts of the image or those parts of the video, the autoencoder will be unable to reconstruct properly. As a result, the reconstruction error in those areas will be quite high. So, based on this, whenever you find that the reconstruction error is very high, we can assume that those are the areas which are abnormal areas. That means such sequences or such data does not normally occur in normal data. So, autoencoders can also be used in abnormality detection. Today, we will start discussing on another very important tool of deep learning, which is convolutional neural network, or in short, these are known as CNN. So, we are going to talk about CNN or convolutional neural network. So, when I talk about this convolutional neural network, we will touch upon the topics of convolution. And while we talk about convolution, we will also try to see what is meant by linear time invariant system or LTI system. We will also talk about what is linear shift invariant system or LSI system. And then we will also discuss about a very similar concept which is known as cross correlation, and we will also try to highlight that what is the difference between a convolution operation and a cross correlation operation. So, let us first try to discuss what is convolution. So, convolution is actually an operator. So, given a linear time invariant system or a linear shift invariant system, the convolution operator actually tells you that if I have an input signal to a linear time invariant system, then what will be the response of the linear time invariant system to that input signal. That means, what will be the output of the linear time invariant system if an input x is given to that linear time invariant system. Now, all the linear time invariant systems are actually characterized by a particular characteristics of that linear time invariant system, which is known as impulse response. I will come to that a bit later. So, first let us try to see what is a linear time invariant system or a linear shift invariant system. So, given any system, let me just draw it as a box. So, this is my system which I am terming as linear time invariant or LTI system. So, if we give an input signal say x t to this LTI system, the output of it will be given by signal y t. So, if it is linear, so when I talk about linear time invariant, you find that there are two concepts, one is linear, one is time invariant. So, the system is linear if the linearity property holds true for that particular system. That means, given an input signal x t or say x 1 t, the output signal is y 1 t, that is the response of the system to an input signal x 1 t. Similarly, if we feed an input signal say x 2 t, suppose the output of the system is y 2 t. So, given x 1 t, the output is y 1 t, given x 2 t, the output is y 2 t. Then if the system is linear, then I must have, or the system must satisfy a property that given an input say alpha 1 x 1 t plus alpha 2 x 2 t, the output of the system or the response of the system to this input alpha 1 x 1 t plus alpha 2 x 2 t must be alpha 1 y 1 t plus alpha 2 y 2 t. So, you find that what is y 1 t? Y 1 t is the response of the system when the input is x 1 t. Similarly, y 2 t is the response of the system when the input is x 2 t. So, when given x 1 t, the output is y 1 t, and given x 2 t, output is y 2 t. So, if the system is linear, that indicates that if I give an input which is alpha 1 times x 1 t plus alpha 2 times x 2 t, the output of the system must be alpha 1 times y 1 t plus alpha 1 times y 2 t. So, this property must hold true if the system is a linear system. Now, suppose a system is having characteristics something like this. So, this is my input x, this is my input y. Obviously, this is a linear time, this is a linear system. Why? Because if the slope of this system, suppose this equation is given by y is equal to m x plus c. Now, given an input x 1, output of the system will be y 1 is equal to m x 1 plus c. Similarly, given an input x 2, output of the system will be y 2 is equal to mx2 plus c. So, now if I give an input which is say x1 plus x2, the output of the system must be m into x1 plus x2 plus c, which is m x1 sorry yeah. So, given an input x1 plus x2, output of the system is m into x1 plus x2 plus c, which is m into x1 plus m into x2 plus c. So, when I have an equation of this form, here you find that value of c is equal to 0, right, as this straight line passes through the origin. So, value of c is equal to 0. So, given value of c equal to 0, this y1 is nothing but m times x1 and y2 is nothing but m times x2, and here this x1 plus x2 is nothing but m times x1 plus m times x2. So, which is nothing but y1 plus y2. So, if this constant c is equal to 0, the system becomes a linear system. Now, if this constant c is not equal to 0, so in that case the characteristics of the system will be something like this. This is x, this is y, and my transfer function here it is given by y is equal to mx plus c, where c is non-zero. So, over here given an input x1, y1 will be mx1 plus c, y2 will be mx2 plus c, and now if you give input as x1 plus y1 x1 plus x2, then my output will be say y, which is m into x1 plus x2 plus c, which is nothing but m into x1 plus m into x2 plus c, which is not equal to y1 plus y2, because y1 plus y2 is m into x1 plus m into x2 plus twice c, which is not same as this. So, though a system having this type of transfer function appears to be a linear system, but actually it is not a linear system, because when I feed x1 plus x2 as input to the system, my output is not the sum of the responses when you feed x1 and x2 separately. Okay? So, this is not a linear system. Now, what is time invariance? Time invariance means that given an input signal say xt, the corresponding output is yt. Now, if the input is delayed by some amount say tau, so instead of t I put it as xt minus tau. So, the input signal is delayed by a delay tau. Correspondingly, the output should also be delayed by the same amount. So, if yt is the output given an input xt, then yt minus tau must be the output when the input is xt minus tau. So, this is what is time invariant, that is, if the input is shifted, the response will also be shifted by the same amount. So, this we talk about linear time invariant system when we are in the time domain, that means my input signal is a time domain signal, it varies with time. But when we talk about images, images are spatial domain signals where the intensity value or the color value varies over space. So, there instead of talking about a time invariant system, we talk about space invariant system, because our signal is a spatial signal, it is not a time domain signal. So, now given this idea about the linear time invariant system and linear space invariant system, let us see what does the convolution mean. So, as we said that an linear time invariant system is completely characterized by its impulse response. So, for that let us first define what an impulse is. So, an impulse is defined like this. So, an impulse delta t is equal to 1 when t is equal to 0, and this is 0 for any other value of t, for any other t, or t is not equal to 0. So, only at t equal to 0 delta t will be equal to 1, and for any other value of t where t is not equal to 0 delta t will be equal to 0. Okay. So, this is what is an impulse. So, given a linear time invariant system, the response of the system to an impulse is what is known as impulse response. Now, given any such impulse to a linear time invariant system, the impulse response, let us consider in discrete domain, at time t equal to 0, so impulse response is h0, at time t equal to 1 it is h1, at time t equal to 2 h2, so on, at t equal to n it is hn, then hn plus 1, and it continues like this. So, this is the impulse response of a linear time invariant system. Now, given any signal, say x n, n varying from 0 to whatever the number of samples we have, we are talking about discrete signals, this x n can be represented as sum of scaled impulses. See, this x n is nothing but x 0, x 1, x 2, it continues this way. Now, what I can assume is, because here I have the value of x 0 only at t equal to 0, so I can consider this as a product of amplitude of x 0 times delta t. This one can be the product of the amplitude of x 1 times delta 1, because delta 1 will be equal to 1 at t equal to 1, and it will be equal to 0 for any other value of t, and so on. So, I can consider my input sequence, which is my signal, as a scaled version or sum of scaled delta functions. So, assuming this and considering the property of linear time invariant systems, I can represent the output sequence like this. So, let us put as, say, on this side I have t equal to 0, 1, 2, 3, say t equal to n, t equal to n plus 1, and so on. So, you are feeding x 0 at t equal to 0. So, with this x 0, we said that the impulse response of the system is given by h 0, h 1, h 2, and so on. So, when you are feeding an input x 0, sample x 0, at time t equal to 0, the output will be given by x 0 times h 0. At t equal to 1, it will be x 0 h 1. Similarly, here it will be x 0 h n, here it will be x 0 h n plus 1, and so on. Similarly, you are feeding input x 1 at time t equal to 1. At time t equal to 0, I did not have x 1. So, it is, I can consider that this is a delayed input, which is delayed by a time equal to 1. So, with x 1, my output will be something like this. So, here it will be delayed. So, I will have x 1 into h 0, which will be available at time instant t equal to 1. Similarly, here it will be x 1 h 2, which will be available at sorry, x1 h1, which will be available at time instant 2. Here it will be x1 hn minus 1, which will be available at time instant n. Here it will be x1 hn, which will be available at time instant n plus 1, and so on. So, considering this way, when I have an input signal xm, input sample xm, at time instant n, my output will be xm into hn minus m. Here it will be xm into hn, and so on. So, considering this, you find that if I want to find out what will be my output at t equal to n, which is nothing but yn. So, output at t equal to n, which is yn, is given by x0 hn plus x1 hn minus 1, continue like this, plus xm hn minus m, plus so on. So, I can simply write this as sum of x m hn minus m, where m will vary from say 0 to infinity if I have an infinite sequence of input samples. Okay. So, what it gives? Apparently, it appears that your impulse response h is flipped because I have h minus m. It is flipped, shifted to n, then multiplied point by point to xm, and then added from m equal to 0 to infinity, and that is what gives you the output at y equal to n. So, when you compute convolution, the convolution is computed by flipping your impulse response and then point by point multiplication of the with the input signal and then sum them up. That is what gives you the convolution output at time t equal to n. So, let us see that what does this convolution actually gives you physically. So, let me assume that in a spatial domain signal, in a two-dimensional case, suppose these are the impulse responses of a linear space invariant system, because we are talking about images. So, these are the two responses, impulse responses of a linear space invariant system, and when your input signal or an image is convolved with these two, what output do we get? Now, before that, let us see that what is the characteristics of these two impulse responses. You find that in the first case, this particular impulse response, come to this last row. What it does? It does an weighted sum of the inputs of 3 consecutive pixel values in a particular row. So, suppose here I have a pixel location, say x say k minus 1, this is x k, and this is x k plus 1. So, this row will simply perform x k minus 1 plus twice x k plus x k plus 1. So, this makes an weighted sum of the 3 pixels. Similarly, this row also makes an weighted sum of the 3 pixels on 2 rows above it and then negate it. And then finally, this entire operator will give a sum of these two. That means, this operator gives you the difference of weighted sum of the pixels belonging to, say, this is nth row and this is the n minus first row. So, it gives you the difference of the weighted sum of these 3 pixels in the nth row and these 3 pixels in the n minus first row, or effectively this gives a derivative in the vertical direction. So, if I put this vertical direction as x, so this is and input signal as f, so this gives you a derivative in the vertical direction which is given by del f del x. In the same manner, you can find that this template gives you a derivative in the orthogonal direction, so which is del f del y. So, these are the physical meaning of these two convolution operators. So, when you convolve your input image with this convolution operator, what is the kind of output that we get? So, given an input image of this form, this is the derivative in the vertical direction and this is the derivative in the horizontal direction. So, obviously, when you take the derivative in the vertical direction, all the discontinuities or changes in the intensity in the horizontal direction, or the edges which are present in the horizontal direction, they will be highlighted. Whereas, if you take the derivative in the vertical direction, then all the lines which are, if you take the derivative in the horizontal direction, all the lines which are vertically oriented, they will be highlighted. So, that is what you find in this case. Here you are getting all the lines which are mostly horizontal, and here you are getting all the lines which are mostly vertical. And if I combine these two, the outputs of two such operators, then this is the edge map, that is what I get. So, in this final edge map, what I am saying, if I combine these horizontal edges and vertical edges, I get the complete edge map. So, this edge map actually tells you some features of the input image, because in many cases the images are the information in the image is actually contained in the edge map. Okay? And using this, your recognition or understanding of the image will be very convenient. In the same manner, if I take say another template, say for example here, if I input image is something like this, and this is one of the convolution templates, then the corresponding output will be this one, where this input image is convolved with this convolution kernel. Similarly, if I take this convolution kernel and with this convolution kernel you convolve this input image, this will be the output. So, here again you find that these two outputs, which are known as feature maps, they gives you the salient features or the structural information which is present in the input image. Here you find that here we have an uniform region. So, here in both of them they have become 0. So, where there is no structure in the input image, in the feature map I do not get any information. Whereas, in all these areas where you have structures, over here, where we have some structural information in the feature map, I have important informations in those areas. So, this is what is convolution. So, what we said is convolution is actually the response of a linear time invariant system or a linear space invariant system to the input signal which is presented to that LTI or LSI system. And we have also said that LTI or LSI systems are completely characterized by its impulse response. So, when I have an LTI system characterized by its impulse response or an LSI system characterized by its impulse response, then given an input signal, the corresponding output or the response of the system will be simply convolution of the input signal with the impulse response of that particular system. So, today we will stop here. Next day we will talk about the other concept, which is cross correlation, and computationally these two are more or less similar, and in most of the cases people get confused between what is a convolution and what is a cross correlation. So, in order to clarify that, in our next class we will discuss about cross correlation, and we will also try to find out that where they are similar and where they are dissimilar. Thank you.